Recording in progress.
Hello?
Hello? Hello? Hello?
Hello, Pankaj sir?
Hello? 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 Hello?
Good evening, Katie sir.
Yes, ma'am. Sabir here.
Hi, Sabir.
KT sir is joining us.
Acha. Okay, no issues. I'm audible and my video is also clear, no, Shabir?
Yes, ma'am. You're visible.
Okay, thank you.
I heartily welcome to Professor Rajesh Kumar sir, who is giving us the very precious time and enlightening us with his knowledge and expertise. Uh, Sir has a great knowledge in the field of the artificial intelligence. So those candidates are working in the field of artificial intelligence. They will definitely benefit it. Okay, thanks once again. Uh, uh, Welcome for sir and I request from the participants that they will take this lecture seriously, so this will be beneficial in the near future. Ritu, kindly give the brief introduction.
Yes, sir. Sure, sir. Once again, I would like to welcome all the respected faculty members and respected Professor K.T. Chaturvedi, sir, who is also the coordinator of this hybrid FDP program, and the student dean welfare of RGPV. Sir is associate professor at Electrical Engineering Department, UIT-RGPV. Today with us for the talk, we have our eminent speaker with us, Professor Rajesh Kumar, sir. A brief introduction about sir. Sir has received his BTech degree from NIT Kurukshetra, India, and MTech degree in Power System, and the PhD degree in Intelligent Systems, MNIT Jaipur. He was postdoctoral doctorate research fellow in the Department of Electrical and Computer Engineering at the National University of Singapore from 2009 to 2011. Currently, he has been working as a professor with the Department of Electrical Engineering, MNIT Jaipur. Dr. Kumar's research interests focus on intelligent system, machine intelligence, power management, smart grid, and robotics. Dr. Kumar has published over 550 research articles, has supervised 25 PhDs and more than 35 MTech theses. He has 14 patents to his name. He received 3 academic awards, 12 Best Paper Awards, 6 Best Thesis Awards, 4 Professional Awards, and 25 Students Awards. He has received the Career Award for Young Teachers in 2002 from Government of India. He is on the 12 journal editorial boards. He has been associate editor of IEEE Axis, IEEE ITEN, Industrial Electronics Technology News, associate editor, Swarm and Evolutionary Computation elsewhere, associate editor, uh, at IET Renewable and Power Generation, Associate Editor at IET Power Electronics, Associate Editor at International Journal of Bio-Inspired Computing, and CAAI Transactions on Intelligent Technologies, IET. Dr. Kumar is a senior member IEEE USA, fellow IET UK, fellow IE India, fellow IETE, life member CSI, senior member IEANG, and life member IST. His area of interest: smart grid, robotics, computational intelligence, intelligent system, machine learning, power conservation and management. And for today, sir is with us, and the topic of discussion sir has taken up is the long-term memory for is the long short-term memory for engineering applications and graphic neural networks for engineering applications. So that is all about our respected eminent sir and Professor Rajesh Kumar sir. Sir, can you uh, uh, speak, sir? Actually, yes, sir.
Yeah, hello. Yeah,
Yes,
am
sir.
I audible? Yeah.
Yes, sir, you're audible, sir. Good day,
Yeah,
sir.
okay, that's
A warm
great,
welcome,
great.
sir. Thank
Okay,
you.
thank you for such a detailed uh, uh, introduction. Okay,
Sir, it's our
I'll share
pleasure
the
to have you,
screen
sir.
and
Yes, sir.
yeah, I'll share the screen and let me know that yeah, the screen is visible to everyone. So
Yes, sir,
is
your
it
screen
okay?
is visible. Yes, sir,
Okay.
visible.
Okay, so now we can start. Okay. So yeah, good evening to all the listeners here and the various scholars from various places. Today our discussion will be in two parts, and the first part is this one, that is basically deep recurrent neural network, a very interesting domain which is building up very fast in the area of forecasting. So what we do in this session, we take the things and steps. A few of the things you are aware of, maybe you are aware of these models also, but yes, nothing bad in getting another viewpoint. So we build up the things, and then later towards the end I'll show you that some applications of this approach also. So I have taken many things from various places, from various PPTs and from various research articles, and combine them so that we can have a good understanding of the topic there. Okay, so to start with, okay, we have a data something like this, which you can see on your screen. Let me take the highlighter also. Okay, so you can see there are three types of there are two figures on your screen. On one we have certain graphical, then some numbers are there and some bar charts are there, and on another we can have continuous graph or some discrete graph or some numbers. Okay, so these are the basically nothing. These are the some data which are taken from. It can be your if you are electrical engineering, it can be from your load data. It can be your wind data. It can be your solar data. It can be some IoT data. Some data are there, and then what we can do with these data. Okay, so say if it is stock data, because stock is very simple, very common phenomenon. So just I'm connecting with it. So what we can do with these data? So one thing is like, okay, I have some data of a stock which is there on your screen, and the question is, somebody can ask you, where will the stock go up or down? Or you can take it like, okay, these are wind data, and somebody asks you whether wind will increase or decrease because our generation is connected to that one. So
So that can be one of the possible question. And another type of question will be that, okay, what type of this stock? Is it a risky or not risky? Is it a safe stock or if it is a risky stock likewise? And then the third type of question can be like, if is the behavior normal or abnormal? So these are the three things which one can ask you, means when, on the data they provide some data, and then from there they can ask you these three things. So when we try to answer these three things, we come out with three different kind of issues and three different kind of category of the solutions. So if I try to address the first one, then it is a basically time series prediction model. Why we could say on x-axis it's a time stamping, on y-axis we have values. So whether the stock will go up and down in future with time, so it's a time series prediction model. So if I try to address this problem, it's a time series class is the time series prediction. If I try to solve the second problem, that what type of stock it is it risky or not risky, then it's a time series classification problem. That is, classification is there, risky, not risky likewise. And if I try to solve the third problem, then it is known as your outlier detection. Basically something is abrupt there, which may not be good, or some outliers may be there or something like that. These are the common things things you will face when you are in industry or in research, where people give you data and then they ask you what to do with these three type of data. Likewise, we have many another problems. Okay, like you can see this on your screen. Okay, on one axis you have certain kind of frequency in kilohertz, and then we have stampings there, and these are the different frequency ranges with different stampings, and then we try to find it out that, okay, what type of bird it is. Okay, can be type of a classic connecting the things, predicting the things, what type of bird it is. It can be a like your ECG signal problem. Okay, on one axis we have time stampings, on another axis we have certain kind of voltage signals, and then we can do, okay, what will be this signal after 10 seconds? That is one kind of question. Second kind of question is whether, okay, this signal is of a healthy person or not a healthy person. That is second kind of this thing. Third can be that, okay, if there is certain kind of problem with the signal when we are recording it, or if this signal is genuine or not. So this one is another type of application where we can see all these things there. Similarly, in electrical engineering, if I talk about, okay, we have certain kind of data, and then we try to find out, okay, rest of the things there, where we need to forecast the things. And that is one why machine learning is very important. AI is because we, from the past data, we try to predict what is going to happen in future. And if our models are very accurate, so then our predictions are good, and then we can take decisions in advance, so that we can prevent if something bad is going to happen or something like that. So all these are the predictions values, that, okay, how the amplitude versus time, or prediction of the birds, or prediction of the moods, or prediction of the swing of the moods, prediction of the when a person is speaking, then prediction of the depression, and many more things can be done. So all these are, you'll find that on one axis there are time stampings, on another axis we have certain values there. And the question is, if this is the scenario, then how we to go for the prediction? Okay, so that is basically the today's agenda, that is forecasting, is how you can forecast the things for the future from the given current or past data. So when we talk about the forecast and why we need it, well, in electrical engineering, if you talk about, we have to do a lot of planning, executions, control, operation, all these things are there, and there is always a time lag. So if you want to reduce the time lag, you need to predict the things in advance. Otherwise, there will always be a time lag, because all the machines, all the systems, they have their own time constant, and because of that, there is a lag. So if you want to reduce the lag, you want to make the things real time, then you have to predict the things in advance. And that's why forecasting is required there. And there are a lot of areas. Few of them are like weather forecasting, product recommendations, energy forecasting, stock market forecasting, and nowadays you can think of anything, like people are doing a lot of analysis and all these things based upon the data, past data, so that they can predict it, whether particular model will be successful or not, or particular product will be successful or not, or what will be the good price to sell it. And likewise, there are numerous applications of forecasting models. When we talk about the forecasting models, we have basically four kind of forecasting models. One is physical model. Basically, physical models are they are totally based on the physical quantities. Okay, like if I talk about the wind forecasting, so okay, what is the past wind speed, what is the location, what is the wind direction, what is the temperature, what is the biometric pressure, and we have certain kind of physical equations connected with those things, those parameters, and then we calculate based upon given other parameters, we predicted, okay, what is the value of wind. Here the problem is we need to make many assumptions there, because when we talk about the physical equations, we have to make certain assumptions. So the bad part of physical model is there is an error between the actual and the predicted, and the good part is basically they depends on the direct relations, so they are fast. These models are very fast. The second category is statistical model. Basically works on historical data, but we use statistical approaches like ARMA, ARIMA, fractional ARIMA, and some of the machine learning algorithms are also coming under this category, where we use stats as a main method to solve those things there. Like we find out, okay, what is the mean, what is the deviation, what is the standard deviation, is there any skewness, and all these things there. Third category comes our learning models, where we use all these machine learning approaches like ANN, SVM, GP, fuzzy logic, deep neural network. They also depends upon the historical data. So both these statistical and learning models, they have one advantage, that their predictions are better, they are very accurate, but they suffer from disadvantages that they take a lot of time to get the things done. So both physical models and learning model, they have certain advantages, certain disadvantages, then people go for hybrid. So that one advantage of one model can be compensated by the second one, and likewise. So third is the hybrid model, where we try to combine your physical model or learning models. Okay, so I start with a very simple, many of you are aware of it, and let's understand it. That is basically artificial neural network. And this is inspired from the biological neural networks. In the simplest form, our brain consists of neurons, and then what we do is we get the inputs, and then based upon the type of methods, whether it is supervised or unsupervised or reinforcement kind of learning, we try to understand those inputs, try to figure out what is the output, and in that whole process we update certain things there. Those are known as weights, and once it is updated or the thing is correctly identified, then the weights are taken as like we fix those weights, and when in future if we give the same input, it will identify it. That's the simple way. Let's understand how it works. So say we are passing one image. This is the image of a cat, and say this we are passing to a person or to a kid who doesn't know whether it's what is it. But when we show the image and then tell him that it is a cat, so what is happening is basically you can see these figures, and these are the neurons. Okay, so neurons take the input and they are interconnected with each other. These are known as the layers of the neurons, and this is the output. And the output is just say cat. And when we say that this is cat and then the kid learn, then what is happening in the brain is you can see that, okay, some of the connections, they are very light, some are very bold. That means these are the weights. Basically weights means the connection is so strong between this and this neuron, and it is weak here, it is much strong this way. So mathematically what we can say that these signals which are going to the input, they are mapped by using these weights in such a way that the person can identify that this is a cat. And this way of updating the weights for a particular input output pattern mapping is known as training of the network. And once the network is trained, then we can test it, or we can pass when we pass a new image, it will recognize whether it's a cat or something else. Well, so these are the things there. It is inspired from the brain artificial neurons, and then how the processing occurs there. Some part of it, some segment of it. Otherwise, it's very complex structure. But one segment of it, that is how the things are happening there in the neurons. That is mapped here, that is mimicked here, and we call this one as artificial neural network. I'll show you one example how it looked like. Okay, say this one is one kind of, this graph or this figure represents something. That is, I want to predict what will be the PM 2.5 of a particular day. Okay, so you can see here, this is the output. And what I'm giving it, that is what is the PM 2.5 day, one day before, what is the temperature of the day, maximum, what is the minimum temperature, what is humidity, what is the wind in X direction, wind in Y direction, day of same day last year, same day last week, and likewise. So all these are my inputs. And you can see that inputs are multiplied by something here. These are the gains, these are known as weights there. So we take the input, multiply the weights, and take the sum of all. Okay, so you can see here the equation Wji into xi, that is all inputs multiplied by different weights, and we add certain bias of it. So that will be this equation, and then we pass this equation to a nonlinear function. Here the nonlinear function is log sigmoid, it can be any function, and then again a weight, and this process keep on doing depending upon what is the structure, which finally give me the output. So how it occurs, we pass the data, known data which are known to us. Okay, so we give some known data here, we assume certain weights, calculate these values, and we check the output. So we receive certain output, and then we compare this output with the actual one. So there will be some error. Okay, so what we can do if there is error, what we can do is, we cannot change the structure of this architecture of this. What we will do is, we change these weights in such a way that the output error is reduced, it is 0. Once it is done, then we can say that our network is trained, and then we can use it for any kind of a prediction. So this is how this neural network works. Okay, so there are various learning rules are there. Learning rules means how you update your weights. There are many methods are there which are available. Some of the common are gradient descent using back propagation technique. A few of the things I'll explain while presenting some more complex structure of it. Application, I told you there are many applications there. Okay, so this is the way how we represent it. Okay, we give an input goes to some calculations here. Okay, they are multiplied by weight, passed through a nonlinear function, and that gives certain kind of output. Well, this one, since you can see the arrow direction, it is only one way traffic, input to the output, and that's why this one is known as feed forward neural network. There is no any feedback loop. That's why this one is feed forward. It works fine, but it has a problem. And the problem is, since there is no any feedback mechanism here, and there is no kind of a memory kind of thing there. And that is the issue with this one. So what modifications can be done? People thought of doing some modifications on it. Let's understand it, how it is happening. Okay, say I want to develop a neural network. Okay, and the job is just focus on the problem. Problem statement is, if day is sunny, then there will be a party. If day is rainy, there will be no party. And now you develop a neural network that if I give any particular day, it give me the output whether there is a party or not. So how it is working? It's we do hot encoding. Hot means we represent your sunny day like 1 0, rainy day by 0 1. Okay, we use certain weights, we multiply this 1 0 by certain matrix, pass through some nonlinear function. So when you multiply it, it gives me certain values like 0.7, 0.2, 0.1. And then we pass through some nonlinear function. In this case, what we are doing is we are making the highest value as 1, rest as zeros. Okay, and that we represent as a party. If it is 1 0 0, that means party. If it is 0 1 0, then there will be no party. So the weights are these weights, W is chosen in such a way that if you multiply 1 0, it will be 1 0 0, and if you multiply it by 0 1, then the output will be 0 1 0. And that's all in the neural network. This is just a simple kind of arrangement. So what we are doing is we are mapping these inputs, this one, with this output. Okay, I'm taking few of the slides from one of my friend and use those things here. Very interesting example he has put it, which help us in understanding it. Okay, and also help us in that, okay, understanding where are the problems. So say this is my structure. Okay, where is the problem? So my structure is like yesterday activities I'm running, and my day, if my day is sunny, so my today activity will be cycling. Okay, if I did cycling yesterday and day is sunny, then I'll go for swimming. And if yesterday it was swimming and the day is sunny, then I go for running. So it is a cyclic process. Basically, you can see that running to cycling and cycling to swimming and swimming to your running there. You can develop a simple neural network. One input, you give the day, type of the day. Second input, you can give the what happened last day, and the output will be the today activity. Okay, it is fine. Okay, but what will happen if it is rainy day? So if it is rainy day, I'll do nothing, I'll sleep. Okay, so this one is also very simple. So one input, you can give the type of the day and activity. This today activity is the output, and yesterday activity is already there. But the problem is this one. Problem is here. Okay, a small problem, one step problem. Like, okay, yesterday I was sleeping, day is sunny, and then what I'll do? So there is some kind of a memory. If it is there, it can recall it. But if case is like this is a typical problem. First day, okay, I was running, then day is sunny, go for cycling, day is sunny, go for swimming, then rainy, okay, sleeping. Fifth, rainy, sleeping, and now sixth is sunny. Then what will be the output? Whether the output is swimming or it is cycling or it's running, and that create a lot of problem then in practical case. And this is a problem for feed forward network. Since they don't have memory, then in that scenario, they cannot predict such type of cases. Then people thought of it, and then they suggest that, okay, what modifications can be done there? There are many examples. Okay, one example is there. Some examples I'll take, that the food was really good. Okay, and then okay, somebody want to take the sentiments from this. Okay, so how to classify? So what they do is they take the word by word. Okay, the first word is it has certain connection with the food, and then there is a connection with was, and then really, and then the last is good, and then they classify it whether it's a positive statement or it's a negative statement. Okay, but it is memory is very important here. Okay, so that is something like when we talk about in computer science, sentiment classification based upon the text. Like you have Twitter data, and based upon those data, you want to classify whether the person is thinking good about you or bad about you. Okay, so some more on this one. That is basically this example. Again, I'm taken from Sugai PPT's part. That is basically, I have two things here. Now you can understand very easily from here how the matrix multiplications and all these things help us. So there are three foods. Okay, you can see here. One is cake, another is burger and chicken, and there are two types of days there: sunny day and rainy day. And then okay, we can represent these things in terms of some numbers, hot encoding. So sunny V10, rainy is 01, and these are the three foods. So we can make it 0, 100, 010, and 001. And now we do the things like this thing. Okay, we need to map it. Means like we need to find out a matrix. This one is known as weight matrix, in such a way that okay, if day is sunny, then it give me the food. Okay, food like this. So I need to find out this matrix. Okay, how to means question is, if you go by the question is that okay, if day is sunny, then this person will cook this food. Okay, and if day is rainy, then this person will make a burger. That's all. So depending upon the day, we have to find out okay, what will be the output, what will be the food. That's the interesting part. So what we'll do is we'll take the input, that is 10. We need to find out this matrix, which we call as a W matrix or weight matrix, such that if I multiply these two, then the output has to be 100, because we say that day is sunny, then output is your cake. As well as at the same time, if I give the second input, then it should give me the second output, but the weight matrix should not change. It's not like it will change every time. Then it's a different story, but weight matrix should not be changed. So you can see here in both the cases, weight matrix is same, but if I multiply it, the input 0, 1, the output will be something different. And that's all. This is basically nothing but a neural network. And we can represent it like this. Okay, I give an input, that is type of the day, and then neural network give me an output, whether it's a burger or it's a cake, likewise. And how we represent it, we can represent it like this. So we have 2 inputs, we have 3 outputs, and you can see 1, 0, 0. Okay, so 1. Now so these are the connection of the weights. So there are only 2, 1, rest are the zeros. And if you check it, say if I give input 1, 0, so 1 goes here, 1 into 1 is 1, rest are the zeros, and 0 goes here and 0 goes here. The output will be 1, 0, 0, and that is exactly this output. This is how the neural network works. Okay, and the second part is what we have discussed. Now these things are in cycle. Okay, first day it will go this, the next day it will go cook this, and the next day it will cook this. So now the things are in they are connected. Okay, well, first day, second day, third day, fourth day, again back here, fifth, likewise. So the things are in cyclic in nature. They have time stampings because now the day is deciding, okay, what is the next, and that depends upon the previous one. Okay, we can do the same thing here, like, okay. So you can see here, this is 1, 0, 0, this is 0, 1, 0. Now my weight has to be 3 cross 3 matrix. So if I multiply this matrix here with this number, I'll get this number. And same matrix, if I multiply by the 0, 1, 0, I'll get 0, 0, 1. So my network is like this. This network is feeding back. So there is a feedback connection. And we call this one as RNN. They are known as recurrent neural networks. Recurrent neural networks, they have a property to store the things there. Okay. It look like this, basically. The output is fed back to the input. And you will find that irrespective now, once this is trained, you give the last input, it will generate the next output, and likewise. You can keep on doing a lot of things there. Okay, you can make it like this also, a combination of both. See, this one is more typical. Okay, this one is cake here. If day is, you can see the day here. What is happening? Okay, so something is happening there. That like if day is this one, sunny, and it is cake here, the next will be the same repeated. But if it is rainy, then it is changing. Then it is again rainy, it is changing. It is sunny, then it is repeating. Then it is rainy, then it is changing, and likewise. Now it's more complicated. Things are cyclic. You can see the cycle is there. Cake is there, burger is there, chicken is there. They are in the cycle, and the cycle is decided by the third variable, which is basically like this. So you can have many combinations there. So if you want to develop this this whole setup, I'm not going to detail of it. You can do all that kind of mathematics there, and finally you come out with this model. That okay, weather is changing here, rainy or sunny, the food is cyclic. And finally, if you do it, you'll find the same kind of the things can be done. And then most interesting part is if you know the day, like okay, 15th day, it was sunny, and then what is the output? Then you can move both sides. You can predict on 13th day, 11th day, or 10th day, or you can predict in future also, because 14th, you can predict 15, 16, 17, like this. So both sides you can move on. And these are basically known as the recurrent networks. So what is the difference between neural network cells? Simple neural network is this one. Okay, you give input and some kind of combinations, it generate an output. But in recurrent neural network, which is denoted by RNN, we have two things: input and output. In between, there is some memory part. Okay, so this one is H0, which is coming in, and it is generating H1. So that's the difference between these two, recurrent network and simple network. So how to write this equation? So if this one is recurrency, basically, used to happen here. So why the name appears and how we can define it? We can say the new state H is a function of, it's a function of W weights. Weights are here in this, and weights are for what? Weights will be xt is multiplied by those weights, and then this ht minus 1 is also multiplied by these weights. What is ht minus 1? This one is old state, xt is my current, xt is my input, w is the weights, and this f is a nonlinear function. This whole will generate a new state. So you can, if you talk about the state, you can see that there is a recurrency, and that's why the network name is recurrent neural network. Okay, let's understand on how it works further, and then we'll see what are the issues with this one. So you can unfold it, because that will give you a better view. So when you unfold it, it look like this: xt minus 1, ht minus 1, yt minus 1, and you can see that this one, you can see here the t factor is coming, t minus 1, you can see here t. This means at tth time, and there is a connection between them. You can see the connection is there between these state, middle one. Okay, there is a connection, and the good part is good part to, you can say, easy part here is all the weights are same in the sense, all the input weights, whether you are taking a t minus 1 or t plus 1, these are the input weights, they are same. You can see here w, xh, xh, xh. Similarly, all output weights are same, and all the weights in between the hidden part, they are same. So the calculations are not so tough, but only the arrangement part is different. Earlier, if I talk about feed forward only, in the feed forward, I have only WXH input weights, and I have only the output weights. There is no WHH part like this. But in the recurrent, this WHH part will exist. That's the only difference. Okay. So this one is again the same representation. Various people represent it various ways. So how it works? Let's understand it. So at t is equal to 1, what will happen? H0, if it is there, it comes. X1 also comes. It goes here to the hidden layer, which will generate H1, which goes to the output layer, like this one. Okay, so at t is equal to 2, next input comes. This information comes from this layer, and then H2 will be generated, then Y2 will be generated, and likewise. So it keep on moving. And you can see here that this is the time stamping, which is very important there. Okay, so let's talk about the calculation part. Okay, mathematics is very easy. See, what are my inputs? You take it like in neural networks. When we talk about inputs are always multiplied by certain weights. That's make it a thumb rule. Okay, so x1 is the input, it is multiplied by weight. So you can see x1 multiplied by some weight. H0 is also input, it is also multiplied by some weight. So these are the two weights, they are multiplied, and both are summed up here. I have shown you earlier that there is a summation sign, and then they pass through a nonlinear function. So here it is 10h, which will generate my h1, and then I take this h1. Okay, because this I need to calculate y1. So again, I told you that anything which is input has to be multiplied by weight. So h1 is multiplied by another weight, and we pass through a nonlinear function which will generate my y1. These two equations, which are there on the left side of the screen, they represent recurrent neural network. That's all. This is all about recurrent neural network. Okay. So this are taken from this paper. So you can say here there are various ways to represent. You represent it like this. You represent in matrix form, like function is 10h, w is the weight, inputs are xt and ht minus 1, which will generate ht, and likewise. And then people did a lot of research on, okay, what should be this function? Some talk about 10h, some about sigmoid, some about some hyperbolic functions, and likewise. You can choose. So that's not today's agenda, but yeah, that's a very interesting analysis. You can read from the books that, okay, what is the effect of choosing your 10h hyperbolic function. Well, whole this setup, you can put it into two ways. Okay, so I'll show it from here. Either you write things like this, or you can write like this. This thing is understandable, but it is there. Say first formulation, weights of your between x and h into x plus weights of h into h plus bias. Either you write like this, or you can do write down all the weights all together and all the inputs all together, and then you write it. So these are the two ways of solving the things. Both are works very well. Okay, so I'm just skipping few of the slides so that we can. So where they are being used. So there are many applications of these RN. Basically, RN can be any of these forms. It can be 1-to-1, that is one input, one output. It can be one input, many output. It can be many input, one output. It can be many input to many output in this formation, or it can be many to many in this formation. What are the uses? The first one, 1-to-1, is the vanilla neural network. That is basic recurrent neural network. Okay, this okay, so let me just skip. Second one is one-to-many. Now this one is very interesting, where it is used. It is it's very popular. That is basically auto image captioning. You give an image here where you can say like a person is a kid is there having a bat and ball. It automatically give a caption that the kid is playing cricket, because the input is one, that is the image, and output is many outputs. So those will be the text sequence of words that the kid is playing cricket likewise. So this one is one of the application when we talk about one-to-many. Another application is many-to-one. Okay, so this one is sentiment classification. Like I give a sequence of word, maybe from Twitter or from social media platform, and it give me the output whether I'm happy about it or I'm not happy about it. Sentiments, whether I'm positive on it or negative on it. So that is one example of many-to-one. Lot of things, lot of people, lot of companies, political parties, they are using this kind of setup to understand the sentiments of the consumers or the voters or something like that. The third combination is many-to-many. Basically, this one is machine translation is a best example. That is basically, I give the input, say in English, and then when I click on it, it will give me the output in French or Chinese or Hindi or some other language. So a lot of such kind of apps you have seen on some seen on your phones or some other platforms. You will find that it's a text to text conversion, one form to another form kind of conversions there. And then the last, this one is basically video classification, the frame by frame level, many-to-many. So I think you have seen nowadays in various online platforms or YouTube, or in your movies also, you'll find that movies going on, and at the bottom the text is coming in certain language, maybe in English or Hindi or Tamil or some kind of language there. So that is basically automatically it is happening. So that is frame by frame it is coming. It is capturing your voice signals and converting into text, and that will be displayed at the bottom. So these are some common examples which people are using there. Okay. So when you talk about many-to-many, so many-to-many, one combination is this one. Okay. We give many inputs and it will generate many outputs there. And another combination can be this, many-to-many. So here we have many inputs, it will generate one output, and then we use one-to-many. So one input and it will generate many outputs. This combination is known as encoder decoder combination. So one part is encoding and the second part is decoding. Okay, so I'm not going to this computational part of it here. Just I skip it. So how it is working, you can see here. So they say the letter is coming C. I want to find out what is the next letter to it based upon certain kind of segments there. So C is encoded like this. So if I have this structure A, B, C, D, E, okay. So the target is, okay, if I pass the C, then it automatically give me the output, or the next letter is D. So we do encoding, that means the input is rest are zeros, it is only one that goes here. Then the next thing is H comes from that side, say nothing is given, so we'll take all zeros, both are multiplied by the weights there, and then these weights pass through a nonlinear function, which give me this one as new h1, and then I'll take this h1, multiply by the weights, pass through another nonlinear, which give me the output y. And here, if I go the output, you can see here the highest value will be 1, so it has to be 1 here. That is giving me E. The answer has to be D. That means there is certain error in it. Okay, so to reduce error, what I'll do, I'll vary this weight with x1, weight with h1, h0, and weight here of h1 in such a way that this recognition shifts from this point to this point. That means highest value will be here, which is equivalent to your D. This is how this recurrent neural network works. Okay, so they can be like in a combinations like this. Okay, this one is a simple RNN kind of structure. They can be bidirectional. Okay, from left to right and right to left. They can be stacked over each other. You can see here that the output of one can be the input to the next, and they can be bidirectional also, stacked and bidirectional. So all combinations that exist in the literature, that how this these arrangements can be done there. So two things happen in all the networks. That is, there is a forward pass. That is basically we give the inputs and move towards the output, and then once we have output, we find the error, and then we take that error back in such a way that we update the weights so that the error is reduced. So forward pass and backward pass. So forward pass is very simple. You can see here x1 and h0, they are inputs multiplied by weights, pass through a nonlinear function, give me ht, pass through another weight multiplied by certain weight, pass through another nonlinear function that will give me y, and then I'll check it this y with the this y which is here with the actual one. This will give me the error. Okay, then I use certain kind of error function, and then my job is to minimize this error in such a minimize this error. And my variables, what are my variables? I can x1 and h0, they are not my variables, they are the data points. Okay, y1 depends upon certain quantities, h1 is just calculated, so only the variables are the weights. So I vary these weights in such a way that this error is reduced. Okay, so this is how the things works there. Okay, so in another presentation, another way of presenting the same thing. Okay, I'll now just focus here. This is, I think, towards the end of RNN, and then we go for the next part. I take the input, multiply by the weights. I take another weights multiplied by h. I sum them up. I pass through a nonlinear function that give me h dash. I take h dash multiplied by weight, pass through another nonlinear function that will give me y. And that's all about your recurrent neural network. Please note here we are ignoring the bias. Otherwise, we add the bias also. That's all here. Okay. So these are the certain same thing, but yeah, I'm skipping because we need to now address many more things. So now the point is how to update my weights. Okay, and that is really basically that is a really interesting point here to understand. So we do in updating the weights, what we do is we find out what is the loss. So this is my loss. Loss means what is my error. And then what we do is we try to minimize it. And we know that in calculus, okay, how to minimize and maximize, find out its derivative with respect to variable and then solve that equation. So we need to minimize this L. So we take the derivative of L with respect to weight. So this is basically what we have. We take the derivative of L with respect to weight, and then we use chain rule, because this L, because what is happening? I'll go back here and just check it here. Go back. Yeah. Okay. Error is here. So if I have to take its derivative dE with respect to the weight, say this weight with x weight, xt weight. So how to calculate the derivative of E1 with respect to x1? So we can use chain rule. What do? We take the derivative of E1 with respect to y1, then y1 with the h1, and then h1 with x1, and likewise. So that is exactly what it is being done here. Sorry, this L with y, y with h, and like this one is known as chain rule. And the another way to see is the error which is at the end is propagated back. This one is known as back propagation technique. Okay, so that is how it is occurring. Okay, this one is mathematics, so it is given almost all the books there. I'm just skipping it here. And what is the now? What is the problem? And what? Let's take it from this problem. This one. What is the problem with this neural network? This kind of a recurrent neural network. This kind of a structure there. The problem is this one. This is the same. I have opened the RNN. One input. I have not taken here H0, but you can see here this is connected. So H0, H1, H2, H3, H4, H5 like this. So inputs, they are all to every block. There are two inputs, X and H, and one output here. Okay, and this output is again multiplied by weights. You will take output Y. What is the problem is very interesting here, and the problem is like, okay, I want to calculate the value here at this instant, this red point HT plus 1. And let's assume that the weights here, these weights, say these weights are the value of these weights, since they are same, so the value of this weight is say 2. Okay, so what will happen? That is, if I take this input x0, so this x0, and let's assume that all the functions are linear. So this x0 will contribute here 2 times. Okay, and then it goes further, then its contribution is 4 times, then goes further 8 times, then goes further 16 times, 32 times, 64 times. It keep on increasing. So x1, x0, which is here, it will be contributing here if it like 64 times, whereas xt, which is this one is contributing only 2 times here. And now let's take this problem. Say right now the temperature of say Jaipur is say 28 degree. So this one is this place. I want to predict, okay, what will be the temperature after half an hour? So what is your call? It has to depend right now, or it has to depend upon what was the temperature 3 days back in the morning. It has to depend more on what is the current temperature. What is the current temperature, which is 28. We expect that, okay, after half an hour it may increase or it may decrease, okay, another 1 degree. It's okay. But if I say that, okay, no, we what is more important is the temperature of 3 days back at 10 o'clock. What is the temperature? It depends more on that. That means our models are not correct. And that is exactly happening here. This x0 is nothing but 3 days back, 10 o'clock. And this one is contributing more because every time it is multiplied by 2 everywhere. Whereas this one is only multiplied once. Now this problem is known as exploding gradient problem. And on the other side, if my this product, this gain, this weight is say less than 1, say 0.5. So what will happen? It is 0.5, it's 0.25, 0.15. After some time, there is no importance of this value, which is also not correct. This is known as vanishing gradient problem. So if my gain, if my weights, those are more than 1, it's exploding gradient problem. If the weights are less than, if the multiplier is less than 1, then it's a vanishing gradient problem. So that is basically this problem. Vanishing gradient, if it is less than 1, exploding gradient, it is more than 1. What is desired equal to 1, but then in that case training are issues and lot of other issues are there. So these RNNs, recurrent neural network, they suffer from this vanishing gradient and exploding gradient problem. So then what is the solution? Because practically it has to depend upon both. It has to depend upon my current and some past values also. So then the researchers propose a new approach, which is not very new, it's very old. but because of computing developments and all these things, these become very popular, and those are known as long short-term memory, LSTM. It was introduced long back in 1997, but it became popular because of the advancement in computing and all the structures there. So long short-term memories, and it overcome the issues of exploding and vanishing gradient problem. So what they have done smartly, that instead of that, where is the problem? Problem is basically here. How much it is going in? Okay, this is one point of problem. Another problem is how much is this is transferring, and the third problem is how much it is going here. So there are three communication channels. They put three gates here. Gates mean walls. They control these walls. Okay, by controlling these walls, controlling these gates, they control the gain, and by with that they can make the things feasible. Means they get rid of vanishing gradient problem. So they put three gates: input gate at input, output gate at output, and forget gate means in the memory part. Let's see how it works. So they are modified versions of RNN, and they have introduced one memory cell. I'll go directly to that part. So they have introduced this cell, you can see on the screen. Okay, this one is a new version, new thing which is introduced, CT. This one is memory lane. This part, let's understand how it works. Okay, so first is they put three gates. Okay, three gates there, and gate means which can be controlled. Okay, so I come to that figure. Let me go to the main figure there so that we can understand it from here. Yes, so you can see here in this case, in this figure, you can see here there are three multipliers. One multiplier is this one. Where is my pointer? This is known as your forget gate, because this line, upper line, we call it a memory lane. So if I put a multiplier here, then I can control this memory lane. If my multiplication is 1, then whatever is coming from the back, it goes as it is. If it is more than 1, then it is amplified. If it is less than 1, then the value will be less. So that means I can control this one. That's why this one name is there as gate. And forget means because this is controlling the memory part here. So forget means if my, say, multiplication is 0, so nothing will go forward, everything stops here. That means I forget whatever is the past. Okay, if the value is 1, I'm taking as it is from the past. That means I remember everything and I'm considering that. Okay, so that is basically this controlling part here. So we have two types of memory. Actually, the idea comes from there. One is long memory, which is we carry from very past, and another one is short memory, which is very recent memory. So then we have to consider both, some combination. Okay, the combination can be done here. Then you can see addition sign here. So this line, which is coming from before this addition, it is coming from long, which is coming from the past. And the second thing is added here. This one is our new memory. And then this combination move further. That's why the name comes long and short-term memory. Now the important question is how much of the long you want to use, how much of short you want to use. So you need some wall there, you need certain gates. So you can see there are two gates, one gate here for long and another gate here for short. Okay, and then this one is output gate. How much you want to put that, pass it to the output part. Okay, so you can see here that way it may look a bit complex, but it is not so. See, this one is H coming from the past, like earlier case. This one is X coming. They are multiplied by a certain thing. Now the question is another very important question. Now who will decide that this value, how much gate to be open? So one way is we do manually, which is not very accurate. So can we make it automatic? Okay, so that is done by here. So what is done here, that H, which is coming here from past, multiplied by weight, added to the weighted of X, passed through a nonlinear function, This nonlinear function output is between 0 and 1, and it will decide that how much gate to be open. Same thing moves further, that weighted value of x, weighted value of h pass through this nonlinear function will decide how much of this. The memory part is updated by 10h function. I told you earlier also in LSTM, 10h we pass through nonlinear function. So that give me the sort memory. And then the added part goes further. Again, we pass through another nonlinear function, which has to be output. But again, the gate is decided by again a nonlinear function. And likewise. Now we have 3 gates. We have weights, and they automatically arrange the things so that the problem of vanishing gradient and exploding gradient can be solved there. So this is the way of working here. CT minus comes in, HT minus comes in, and they calculate what is this value, and that value controls the gate, and the second value control the second gate. So 4 gate is controlled there, and then input gate is controlled there, and the output gate is controlled there. Okay, so when you compare both RNN and LSTM, there is only small change. See, this unit, this and this is everywhere. Okay, this is this unit, central unit. This arrow, XT, 10H or here. So this is this part. But we have put 1, 2, 3 gates. So this one is a bit modified. And this is known as LSTM. Okay. And then people come out various variants of LSTM. Like in 2000, this one of very interesting variation comes in. They are known as peeping. That is peeping. What is peeping? This is that, okay, the gate must have, instead of having 2 inputs, it must have 3 inputs. The old memory should be also a part of it. So they take the old memory and then add to it here in decision making. That is known as peeping. So how it works, let's understand. Okay. So LSTM in XT goes in, and then we have, instead of 2 inputs, now we have 3 inputs. In RNN, we have XT and HT minus 1. Here we have XT, HT minus 1, CT minus 1, because we are considering 2 memories. And then it will generate 2 outputs, CT and HT, and from there you can generate a YT output. And what is the agenda here? Agenda thing is C changes slowly because this part. So we call it a long memory because that update very slow. H changes faster because it's a short memory, and then we can make a balance between short and long memories to predict our things in a much accurate manner. Okay, so so now the pictorial representation looks a bit complex, but let's see the equations. They are not so complex. So what we have inputs, XT, okay, HT minus 1 and CT minus 1. Okay, now let's see the things are repeated. I'll take XT and HT minus 1 multiplied by weights, pass through a nonlinear function, I'll get value Z. Okay, so say I'll get one value Z. Then again I'll take XT and HT minus 1 multiplied by some another weight, WI, and I'll get ZI. So I put it here, ZI. Then again I will take the same inputs, XT and HT minus 1 multiplied by another weight, WF, pass through another nonlinear function, say I get a ZF. And then again I'll take the same, so I put it here, and again I'll take XT and HT minus 1 multiply another weight, W0, pass through a nonlinear function and say Z0. So you can see what are these. Z is this value here, ZI is this gate value here, Z0 is here, and ZF is here. So we have 4 values there. What we can do is further. So it's a ZF is forget gate, it's a input gate, this one is updating information, this is the output gate. Okay, and then what if I add CT also into the calculation, then this one is nothing but a people. Okay, this is people. Instead of 2 inputs, I have 3 inputs now in people, nothing much more than that. Okay, so what we will do, let's go again with the LSTM simple. So I am multiplying, you can see here Z and ZI. Okay, here, so I have multiplied here, and then I'll take CT minus 1 and multiply it by ZF, which is here. Okay, and then I add the output of this and this, which is here, and then I'll take CT from here, which goes away, and then I'll multiply it by 10H and multiply with Z0 here, and that will be my HT. That is at instant T, and then I'll get a YT also, and then I add another to it, same, that will be at T plus 1, and likewise I keep on doing. This one is how the LSTM works. Okay, I hope this thing is clear to everyone, how the LSTM works there. Okay, then people, okay, now just quick over a few more things, and then because for this session, for this lecture, how much time left? Can anybody suggest?
Sir, we can, if you need some break, sir, we can break for 10 minutes now, and then we can resume. Otherwise, if it is comfortable for you to continue, then we can continue also, sir.
So let me, there are two parts. So for
Yes.
one part, how much is the time?
Sir, it is from 7 to 8, then from 8 to 9, and
Okay.
from 9 to 9:30, we will have the question answer session, sir.
So what I can do is, okay,
Yeah.
I finish this topic in next 5 minutes, then we'll take a break of 10 minutes, and then we go for the next part.
Sure, sir, sure.
Okay, so just giving you idea that because people come out with new combinations, this one is another variant or new some kind of change in the LSTM. Basically, they say that, okay, this section controls the old memory, this is for new memory, then the sum of both has to be 1. Why to put a new switch here, new control calculation? Just put whatever the value calculated here, 1 minus that value will be the controller here. That means if my output here it is 1, so if 1 means I'm taking old memory as it is, then the current memory has to be 1 minus 1 0. There should not be any current memory. Or if I take it to 0.5, then 50-50 of both and combinations like that. The advantage of doing this thing is, okay, my weights and calculations reduces because I'm not taking any switch calculations from this side. And this they call as a coupled forget gate. Coupled because your forget and input gates are coupled here. Okay, so they are coupled. They depends on one parameter, both these gates. Whatever be the output, 1 minus that will be this output. So that is one part to simplify the equations, and then further they will do some more changes. And this is what Chow reported in 2014, and which brings a lot of change in the research community. That is GRUs, which replace your LSTM. GRUs nowadays are very common, so they modify. So you can see here LSTM. What they have done, they have combined the earlier versions of LSTM. So this one is basic LSTM. You can see that one minus comes from the coupled part. You can see that H is coming into the calculations everywhere, the memory calculation that comes from p-pole. But the good part here is, if you compare with GRU with LSTM, in LSTM we have 3 inputs, one here, the second here, third here. Here only we have 2 inputs. Okay, 2 inputs. Okay, and the gates are the same. You can have 3 gates here. Some of them are coupled one. Okay, these are the coupled gates. So the calculations have become a bit simpler. It's much simpler than the your LSTM because of the reduction in the number of the inputs. The weights also reduces. It's more fast also, and it also carries the properties of your coupled gates as well as p-pole gates. So these are the this one is very interesting area where people are working, and that is gated recurrent units there. Okay. So coming to the application part of it, one application I'm showing you here, we have done some work on, like we have taken data of Jodhpur location 2015, and there were around 8,760 samples with 5 features, and features are wind speed, air temperature, pressure, dew point, and humidity. And the job is to predict the next part of next wind speed. Okay. So if you plot these graphs, nothing is very clear from this one. These are the specification of the turbines which are being used in those areas. So this is very important part, how to do it practically. So you start collect the data, normalize and standardize the data. This is very important, because what happen is some data are of very big values and some data are of very small values. So what will happen, because of that there is imbalancing. So you have to, if you normalize it, then all will come on the same scale and your model will be much better. And then you have to select the features, what are the good features for you, and then you divide the data. So divide the data like in two categories, training data and test data. And again, you divide your training data into two parts. One is training data pure, another one is validating data. So what you do is you take the training data of here, use these data to train the algorithm, to update the parameters, and then validate on those setups. Once that is ready, then you test it, and finally you have predictions there. Likewise, okay. So this is you can see here the graphs, training and testing, they are okay, but yeah, we calculate it like this. So you can see here, these are the different methods, ELM and NARCS, and this one is LSTM, and LSTM is performing much better than the other algorithms. Later on we proved that okay, GRU perform better than LSTM, and people keep on doing all these things there. So this one is just a wind forecasting, application to the wind forecasting, which can be used for electrical engineering. And yeah, okay, I'll stop it here. Yeah, we'll take a break of say 10 minutes, and then again I will start with 8:25 with another interesting machine learning technique, which is graph theory based, and which can be applicable in various areas, and we'll see that how good is that particular approach for computer science people or electrical engineering or medical science people. So let's have a break of few minutes and 10 minutes, and
Sure,
then
sir.
we will join back.
Sure, sir. We will break for 10 minutes and then we will resume at 8:25, sir. Okay. All the participant kindly resume back at 8:25. We will be having sir again with us.
Hello, can we start?
Yes, sir, sure, we can start, sir.
Okay, okay. Okay, welcome to the second session. Here we talk about GNN mainly. This one is some work which was done by my student. I'll explain this work also, very interesting work. But let's understand what is GNN, that is graph neural network, and lot of applications are there in electrical engineering. So we try to understand the basic concept, the theory, some mathematics, then how, what are the, why people go for it, and then we'll see that how people are implementing it, and then some case studies are towards the end of the session. Just 1 second. So you can see here when we see the things, when we check about the data, they are in graphical form. Graphical form means each point is, each node we call it, it has certain kind of features. That node can be represented by certain kind of values. Like if I talk about electrical engineering power system, so each node is having your P, Q, V, and delta. Likewise, if I talk about a social graph, each person who is we have like a node, it has certain kind of features, and then they are connected with each other. Somehow they are connected with certain kind of features there. Okay, so this one is one case. Similarly, like we have transportation graph, so we have source and we have destinations, and we have and connection between the source and destination. Similarly, like brain graphs, each node represents certain kind of activity operating unit, and then they are connected with each other. Similarly, web graphs, molecular graphs, gene graphs. So this one is a interesting viewpoint to see the data as a graph, and then try to figure it out that okay, what we can take it from here, and then how we can infer the things from there, and that opens a combination of your geometry, your features, some mathematics and computation form, and the domain is known as graphical neural networks. I'm taking few examples here, taking certain pictures from various places. Like, okay, we can club them, we can cluster them based upon their properties, like online friends, family, and high school. And they have certain properties there that, okay, this one is a person, this one is a boy or a girl, reading in particular school, reading or in particular college, reading in this year, with these subjects, and then these subjects are connected with another one, and likewise, like you can see here, these are the persons and they are connected with each other. And the good part here is, if I know one point, okay, this one at the end, and if this is well connected graph, then I can trace based upon the connect properties, and then I can find out the link with any of the person who is connected in this graph. The social graphs are very common. You can see all these things happening near around. Maybe you are not like now you are not seeing those things that way, but yeah, you see that if you are just 1 second. Just 1 second. Hello. Yeah, hello. हाँ अभी एक मीटिंग में बाद में बात करते हैं. Okay, so you will see that okay, if you have any account on like social media like Facebook or all these things, you'll find some one can say some pop-ups on your Facebook page, or likewise, okay, can be your friend, or he or she can be your friend, or some recommendations are coming. That is because they try to find out the connections between the people to people, and then based upon they recommend it. So this one is one kind of representation, which is social graph. This one is a traffic map of any particular city. So you can see here, or all these points are the junction points where traffic are coming from any different directions, can be taken as node, and then these nodes, they are connected with each other. So if I have information here, then I can go back to these particular paths, and I can find out the information at another end. So this one is traffic as a kind of a graph there. Optimization problem. This one is TSP problem. So TSP salesman problem, that is, these are the cities the salesman has to visit and in such a way that it covers the minimum distance. That kind of structure is there. But yeah, this one is again a graph because the cities, they are connected with each other, and then how you solve that problem, formulate the problem, solve the problem is a testing domain to work. Medical diagnosis is full of it. Okay, if you can check it, okay, this one is the endpoint. If I go by this graph, okay, so there is some kind of phenotypic abnormality with a certain person. So then what are the possible things there? That it can be abnormality of the eye and abnormality of the face and neoplasm, and then I go back and then I can check it out. Okay, what are the things which are present there, or other way around. If I can, if I find something, say this property with some person, and then I can move on, and then finally keep on tracing these features, and finally I can say that okay, this can be the ultimate effects. And likewise, drug discovery is full of it because the molecules, we find that they form a particular graph. Okay, so this one is a molecule, and this molecule can be taken in form of a graphical, that okay, your H, how H is connected with O, and O is connected with other H and pairs, and likewise. And then can it be a good drug for a particular virus, or likewise. So people are using this this kind of approach to go for drug discovery methods. This one is a drug discovery. You can see the landscape, it is quite big, and they are doing a lot of things. So one kind of application is this at the bottom, you can see. Okay, so you have one kind of medicine here, another kind of medicine there. So this medicine has its own graph representation. The second also has some graph representation, and then we try to map it, that okay, the new drug which is being proposed, that has some kind of side effects or not, because the similar kind of a drug has certain kind of a side effects and all these things. So not only in the drug discovery on this left hand side, but yes, it can be used for the other part also, like what are the side effects, where it is affecting, because in drugs we have a lot of complexities, how the drug is interacting with the protein, how the protein and protein, they are interacting with each other, and likewise. So this one is having a lot of application in drug discovery. One example is this one, which we have already seen and during COVID, like okay, some person is there, okay, and then how many person in contact with, and then how they move, and then where they reach, and likewise. So this one is a simple graphical representation which help us in modeling that how the COVID is spreading. And this one is again a graphical representation. So this one person and is in touch with the 1, 2, 3, 4, 5 near rounds, and then the second day, or we can put the cycle, then next this person moves from this place to this place, and then come into contact with these 4 persons, and likewise. So this one is another application where you can use this technique. Recommended system, you'll find a lot of online purchasing houses, Amazon, Flipkart, and many more are there. So you'll find that you're looking for something, and then you go down on the same page, you'll find a lot of recommendations are there, that okay, this person, you're looking for the similar item is this one, or what you have purchased, some person has also purchased this one, and likewise. So which one is good, which one is bad, and likewise. So there are certain connections between the things, and based upon that, the recommendation system works there. Similarly, you've seen graph generation. So like yes, one we have seen already in LSTM side, but here it is a different way, that it identify, like in this picture, that there are mountains, and there's a horse, there's a cap, shirt, face, and then it try to find out, okay, face, and then horse, then face of what. So it adds certain things. First it identify face, mountain, man, hat, shirt, and likewise, and then try to fill the things there. Then It can put it face of horse or mountain behind horse, man riding horse, man wearing hat, man wearing. So that is basically both ways. Either you have seen, you go for text, or if you have text, then it generates a scene for you based upon the data if it is given there. Like here, I have vase, so it's start with vase and then vase with floor, okay, and then vase with floor in the vase, so makes sense. So then it will create this scene there, and then vase on table, and then vase on table under, and like table is under the vase, and then table is under the vase, beer is on and table, and likewise, and then it creates the whole scene there. Simply your human object interactions, that okay, there are few things here. If I take this picture, there is a vase, there is a knife, there's a person is leaking it, there's a table, and then we try to find out the phrases and the connection between the various segments there. Similar in the text classification, so we have text, and then this text is breaked, and then they're connected, and then try to find out the similarities, and then okay, classify them, that okay, what is the main information, or many more things can be done. Similarly, relation extraction. Okay, so we have some sentence here. Then what is the relation between the mutation and this part, and this one and this part, and then this one and this part, and then finally can be concluded that okay, what is the main feature of this whole sentence, and likewise. This one is very important in sports or healthcare. People are using it, pose estimation. So I have images. Humans, they can be represented in terms of graph, that joints are the nodes and there are the connection between the joints. So this can be one kind of a structure. And then we have different structures. We focus on certain area, and then we apply these gene and techniques to find out whether what the person is doing. So it is automatically classifying that person is running or sitting or walking or something like that. So we are estimating the pose from there. So many things can be done. So let's summarize them. So we have inputs in terms of nodes and the features there. So then we have graph neural network, and then it do various things. And some of the common things is basically node classification. Node classification is classifying this one, classifying particular node. What is this node? Whether this, okay, about the node, whether the node is good or bad, or it's the, if it is medical healthy or not healthy, if it is something else. So we classify in the nodes. Second one is link prediction, that whether they are connected or not. Okay, and then community detection, graph generation, matching the graphs completely. That okay, if this is one graph, so if this graph is similar to it, then this will represent what. So this one is the first case, node level prediction. So I have this graph like this, okay, and I know how they are connected. So they blue and green, and they have certain values, they have certain features, and then suddenly a new node come in, and which is connected to this one. I want to predict it, the color of this one, whether the color of this question mark is green or it's purple. So if I'm doing this, this is known as node level prediction. Okay, if I try to predict it whether this new one is connected with the purple one, okay, then that is known as edge or link prediction, whether they are connected or not. Okay, so node prediction case is like, okay, these are the people and this is connected to this one, so I want to predict it whether this person smoke or not. So this one is node level, connecting or finding things about a certain person. Okay, similarly this one is link prediction. So maybe about okay, this one is this person is having certain kind of a feature, this one is certain features, if this like a particular kind of video, that then this like or not or something like that. And the third one is graph level, that okay, and this complete graph represents one drug, and there's another complete graph, so we try to find out whether it's suitable drug or not or something like that. So three kind of predictions occurs, three kind of job we can do here: node level, edge level, and graph level. Okay, so the structure is like this, and once it is done, then what we'll do at the end, once the graph is there, we pass it to seeing one layer kind of structures, and then we solve it. Well, they're kind of analogy that, okay, there are nodes, they are taking they are connected nodes, which are the same like a neural network, but and there are weights also. We have weights there on the neural network, but neural networks are very complex. In the structures, the calculations are very big. Here, the structure is very simple there. Another part is, okay, we are working with images, and when you work with the images, there are various approaches like you have CNN and convolution neural network and likewise. What are the issues? Basically, the issues are like, okay, if I'm solving it, this image, this is a cat, but if I take a different image size, then I need a different neural network, because otherwise I cannot do the same like a high resolution image uh, with the same and another image is low resolution on the same structure. If my size of image is different, the neural network original will not work. For a neural network to work, all the data inputs has to be of same structure, which is practically it's a difficult. So if there is a difference in size and shape, they will not perform good, and that is one problem. Whereas this thing works on graph neural network, they work on it. The second type of problem is basically so we can say they are the size these networks are size independent. Second is isomorphism, like, okay, if this is the image, okay, and if I train my neural network on this, and if I pass the image, the same image inverted like this, then neural network will not recognize it. It will give you certain kind of errors. So whereas graph neural network works fine with this one. So likewise, because in your CNN neural network, their structures is like a grid structure, and it's a fixed grid structure. If you do any change there, it will create a problem. It will not so efficient. Whereas in graphical neural network, the structure is flexible. This red color node, whether you put it here or you put it at top, put it left, right, anywhere, it make no difference, but it has to connect it with this green one. That's all. So that's the difference. That's why these algorithms, these techniques are becoming more popular. Like you can see the case here. Okay, you have grid structure. This one is convolution neural networks, so graphical. So that has to they are fixed one. Whereas in this case, you can see it's a flexible structure. Things are happening here, like this node, how is decided by the information from the side nodes. But these side nodes, they are fixed. Here also it depends on the side nodes, but the side nodes are also flexible. So that kind of rigidity is not there, and that's why in many cases this perform better. Well, how it works, let's understand it. This one is very interesting part here. So to understand it, you can any kind of a graphical neural network. You assume it that each node, you represent yourself as a node in this structure. So this one is you, this one is your friend, and likewise. And now you are 5 people, and whatever you 5 you can do is something like you 4 are there initially. Then the 5th is a friend of one of your friend. And then your group has certain property. So you want to find out you want to predict the 5th property of the 5th one. Obviously, there are certain features which will be there, which are common, and that's why the 5th one is connected to you. And from there, you can predict about the 5th one. So same thing is happening. So here, the message passing is one part. Message passing means these are the nodes. They have certain messages, or you can say they have certain features. This one is same like, okay, I got some news, okay, about I read something about certain event happen. I share with my friend. So that is iteration 1. Then he share with his friend. That will be iteration 2. And after 10 iteration, you will find that that news is shared, the spread between 10 or 20 different people. That is exactly the message passing. So message passing means each node here, they have certain features, they have certain news. So green one has this green news, red one has red news, or likewise. Okay, and what will they after first iteration, they share the news with each other. So the second will send something to 1, third will send something to 1, fourth will send something to 1. Similarly, 1 send to 4, 3 and 2, 5 can send only to 4, and 3 can send only to 1 and 2, and likewise. So what will happen that after So then what will happen after first iteration? One will update. So how it will update? It has two things: his own information, his own features, and the information from the neighbors. So 2, 3, and 4. 2, 3, and 4. And based upon this, now here we can apply any kind of a mathematical formulation to update the information at 1. Okay. So like, okay, we aggregate them and then aggregate and then update it. So when you update it, you'll find the information at 1 is a mixture, some of its own, some from 4 its own, from 2 something, from 3, and likewise. And these things keep on happening. This process is known as message passing. There are various ways to aggregate and update the things, but this is the interesting part there. And somewhere it stabilizes and the network is ready for any kind of operation. Okay, so this is how it works. So rest of the work, they also get updated after certain time. Okay, so this one is just, we call it embedding those features into the main part of it. Okay, so I'm just keeping this thing what I have explained to you, and this one is just explanation that okay, after few iterations, then one is also having the red one in the because after first iteration you will find there is no red one. Red only reached to 4, but after the next iteration it may be possible that the red feature comes to the 1. So you'll find that all are having their sharing of the informations and likewise. So the rule for representation or updation is two things are happening there. This one is HU, its own, any node, if you are having its own features, and these are the aggregate of the other features. So now if you are from electrical engineering, let's assume a system, power system. So we have one node, it has its own PV, PQV, and delta, and it is connected to another node. It also has some PQV delta, and if something happens there, then those values after certain iteration will reflect to the first one. That is exactly same happening here. Okay, so we have this one is own features, these are from the neighbors, and then you update the things there. So how you develop a new or you want to develop a new kind of a structure, or what are the various kind of variants there? So variants can be in aggregation. You can aggregate, either you take the mean of the all or max of all. You can use neural network there to update. You can use recurrent neural network to update, aggregate. And for update also you can use mean, max, neural network, recurrent neural network, and their combinations, they develop the various variants of GNN. Okay, so this one is one of the popular GNN structure, which is proposed by Kirf in 2016. So you can see here, it is the calculation is the sum of the normalized neighbors basically. Okay, so normalization of the neighbors, and then weighted normalization of the neighbors, and that is they have considered for updating. Then in 2016, Jahir proposed that okay, your aggregation can be taken by using MLP, that is multi-level perceptron. They have used neural network so to update the values there. Similarly, in 2017, graph attention network comes into the picture. So they have proposed attention weights to the features there. Then again, 2015, Lee proposed gated one. Now you are in earlier lecture we talked about gated recurrent unit, and now they have used the gated recurrent unit as a feature or as an aggregator in this case, and that's why the name is gated graph neural network. It's a combination of GRU and graph neural networks. So this one is a very interesting paper. If you go through it, it's a review on the graph neural network. So I've taken this information from there. It is on RQ. It's freely available. So you can see here, they are the different names. So these are the variants, and the variant depend upon how they are aggregating. Some of them are aggregating like mathematical relations like this. Some of they are aggregating on the basis of like this. Some of them are using concentrators, some are using LSTM, some are using gated units, and likewise. And similarly, you can have updaters. So you can have various combinations to complete this whole structure. Okay, so okay, let me present that mathematic. Let me check it if it is there. We have time, so I'll give you something on mathematical part of it. Just give me 1 second. I'll give you some mathematical insight of it. That will be better. Just wait. Yes. Okay. And what I want to show you is some mathematical formation. Let me see if it is there in this slide. Yeah, it is there. So okay, okay. So how it is working? Let's understand it. This one is graph, okay, which is there on your screen. And if we can talk about some kind of updation of the things there. So if I consider this calculations as this one as a node, if I want to find this node, what is the nature of this node? This is known as node classification problem. If I take all the nodes and then try to find it out, that is known as graph classification. And if I talk about the link, that is known as link prediction. Okay, so now let's talk about the mathematical part of it. A simple example so that everybody can understand it. Okay, so so this is the graph which we want to solve. And let's talk on this one then. So we have, you can see the graph there, and the graph can be represented in terms of nodes and in terms of the links there. So we first prepare adjacency matrix. How we can do it on computers. Adjacency matrix is basically the matrix which represent which node is connected to which one. Okay, so we can write ABCD here, ABCD here. So A is connected with E, we put it 1. Okay, if it is a directional, then arrow will decide that we have to put it 1 or -1. But otherwise, if it is non-directional, if there is a connection, we put it 1. If there is no any connection, we put it 0. Like B is connected to E and D, so both are 1 here. B and D, B 1 here and 1 here. Similarly, you can calculate for C and D and E. This is the adjacency matrix, which give you idea that which node is connected to which one, because your computer will, and difficult to make you understand, it's difficult to make computer understand that okay, this is a graph and so on, but matrices are easy to handle. Okay, then we create the degree matrix, which is known as D matrix. So degree matrix give you idea that how many nodes they are connected with. Okay, so that gives us degree. So see, A is connected to only one node, so it's 1. B is connected with 2, so it's 2. Okay, C is connected with 2, so it is 2. D is connected with the 3, so it is 3, and E is connected with the 4, so it is 4. So we calculate A matrix, we calculate D matrix. Okay, and this is the feature matrix. Feature matrix means each node, this A, B, C, D, each node has certain features. Features can be like, okay, you can take B as a person, and a person has a feature that he's a boy, he's an engineer. That is the second, and the third feature is he's having a car. A D can be a girl, she can be an engineer, she can having a bike, likewise. So these are the features. So these are the features of A, these are the features of B, these are the C and the D and E. And we have to develop a network graph on it. So what we do is basically we multiply. So what we have done in message passing, okay, in message passing, if I have that figure, go back, let me show you that figure also. I'm going back. Yeah, this is what we have done in message passing. See, I want to update it. So these are the features of the nodes. You can see here 3 features. So what I'm doing, I'm just taking the rest. I'm taking all here and taking average of them, and that will be the new feature of this. So what exactly what we are doing? We are doing 2 things when we are not just like adding all these things. What this is not counted here. This is counted, but if anything which is not connected to this node, that will not be counted. Like if I want to calculate the features here, so only two will come. This one, 3 will come. Only this one, and its own. These 2 will not come. But this node, pink one, brown one, is connected with all 1, 2, 3, 4, and cell 5. So we have 5 values here, and we have taken the average. You understand this concept? So indirectly is basically what we can do is, we know these feature metrics. We know that there is a matrix which represent whether they are connected or not. So if multiply them, the same thing will occur. And that is what is being done here. So now coming to that part. So we have adjacency matrix, we have multiplied the feature matrix, and this one will be the new feature of A. First feature. And we complete it like this. So once we have completion, so these are the new updated features of A. So it's very simple. We need not to draw the graphs and all those things just to understand. What we have to do is we have to multiply the adjacency matrix with the feature vector. So we will get a new feature. But now, okay. So similarly, so we have adjacency matrix. What now we are doing here is something more modifications. When you draw the adjacency matrix, the diagonal element will be always 0. So we add a I matrix because why? Because if I take diagonal elements 0, then my own count is not there. You understand from this one. This row represents that there is only connection between A and E. And if I multiply this row with the features of A, so only the effect of E will be there. So A is modified only because of the effect of E. But in reality, it has to be both by A and E. So A is always missing. Similarly, B for B is missing. Similarly, C for C is missing. So to cover that part, what we do is we add identity matrix to it. And then we have a diagonal matrix. Okay, we have diagonal matrix. Similarly, we develop a new degree matrix. Why degree is calculated? Let's understand it. Since now your adjacency matrix is modified, so how many elements are there in this row? There are 2 elements. And say I am applying an average formula. So what will be the average? Average will be A plus E by 2. So how to get that 2? So what we can do is, or in first row it is by 2, in second row it is by 3, average value in third row it is by 3, in fourth row it is by 4, in fifth it is by 5. How to get it? What we do is we modify the degree matrix. So now how many are connected with A itself and 1 more. So this degree matrix is modified. And if you take the inverse of this, that will be the factor 1 by 2, 1 by 3, 1 by 3, 1 by 4, and 1 by 5. So now the things are easy, simple. You take new adjacency matrix, multiplied by the feature matrix, multiplied by the degree matrix, you will get the new features of A. That's all. And once this one is developed, then you make a simple single layer neural network to identify the solution. That is how the GNN works. It's a very simple process. Okay. So this is how it works. So there are various versions are there. I'm not going to those versions, but I will show you some of the interesting results, which I promised you that we have done something good that I would like to share with you. Okay. Okay, so in this case, we have what we have done is we have implemented is for human activity recognition. That is, if I have data, can I recognize whether the person is cycling, walking, playing football, or all these things? These are the various activities there. So what we have done is we acquire the data from muscle signals, and then we apply pre-processing techniques using wavelet theory and all that. From there, we find out the features, and then we develop a graph. And then this graph identify whether based upon the muscle signals, whether the person is standing or it's walking or it's going for a staircase and likewise. So these are the features we have considered, 11 features. 11 features means each node is represented by these 11 features. We have developed a new kind of approach here that to develop the graph, we use correlation, Pearson correlation, whether the nodes are strongly connected with each other or not. And then these are the performance parameters, whether our solutions are good or not. To find out, these are the standard performance parameter like accuracy, specificity, sensitivity, Pearson, and F score. And okay, we have checked it for normal person for 10 subjects here, and abnormal person in many cases it shows accuracy of even 100%. And these are the results when you compare it with like SVC support vector machine classifier, KNN classifier, MLP, and this one is GNN, which is much better than the rest of the some classifiers, both in normal persons. Normal persons means normal persons. We have signals for normal persons and abnormal also, because what will happen, like in normal person, that muscle signal is okay, it's easy to find out, but there are persons who are abnormal where there is a mixing of the signals. Abnormal means they have some kind of problem with knees or ankles and likewise, so it performs well there. So thank you. So that's all about GNN and its part there. It's one kind of application. One of the scholar, he's working currently on implementing your GNN in electrical power system. You can see some of the publications from my website and these PPTs from there. So, okay, I stop it here for the presentation part, and now I'm open for the questions. If you have any query, unmute, you can raise your query or you can write in the chat box. I'll read it and then I'll try to answer your queries from there. Your questions, please. Okay, I'll share you my website. You can download PPTs and various papers and the inputs from this website. My mail ID is there. So if you want to work on these areas or you want to understand few more things, if you have any query, related queries, you are welcome. You write over it. I'll answer your query as quick as possible. So now any question if you have?
Any of the participant is having any queries, kindly unmute yourself and ask. Sir, I don't think so. There is any queries right now, sir.
Okay, it's
Yes,
okay.
anybody want to ask?
Yes, please.
No, sir, I am seeing the participant.
Hello. Hello.
Yes, sir. Sir, actually, that was KT, sir. He was
Ritu.
KT, sir. Yes, sir.
Participant.
Any participants having any queries? Sir, KT, sir, I think so. There are there is no
I think
queries.
so.
Yes, sir.
मीन्स आपको क्वेश्चन कुछ पूछा था तो वो मेरे को सुनाई नहीं दिया. If you have any question, yeah.
No, no. Sir, I want to request from the participant if they have
Okay.
any.
Okay,
Yes,
okay,
sir.
okay, okay,
Sir, there
okay,
is
okay.
Priyambada ma'am. There is Sir Priyambada ma'am. She is
Uh-huh.
asking how we can use deep learning in IDS.
So idea stands for?
Priyambada ma'am, can you please unmute yourself and ask?
Hello. Yes, sir. IDS intrusion detection system.
Intelligent?
Intrusion detection system. This is for for security purpose.
Okay. Okay. So
Yeah.
so then the point is like, do we have any data of the attackers, and then then we can take certain kind of extract certain kind of features from that. If we have, we can do. Because see, whole this structure, whole ML is basically we have what type of data we have, what type of features we have, and then we try
Okay.
to solve it by different methods. Depending upon the type of the problem. Like the previous lecture, we have data where on one side timestamp,
Okay.
on other side we have values. This one we have features
Yeah,
and they are
but sir,
connected.
I
Yeah,
yeah.
please.
Yes, sir. I just want to know, sir, which approach of deep learning so we can use in the IDS.
So approach is decided by like what type of the data, how many data you have, how many features you have,
If, so for example, if we have a banking data, so
right? Okay, so what are the inputs?
yeah. Sir, it's we can take daily transactions.
Mm-hmm.
Yeah.
See, ma'am,
So
we can see
deep
we have
learning
banking
can work
data.
on for we work on ideas, or we can use some other technique, like for
No,
example,
it will work.
from
Let me
machine
explain.
learning or the deep learning. Yes, sir. Go
Let me
ahead.
explain you the various challenges, various things we can solve it. For say there are 4 users, okay, 4 bank users, okay, and then they have their features. Features can be like how their buying patterns, their investment patterns, their incomes, okay, and their age groups, and likewise, and how they are connected with each other. Now this forms a graph. If you want to solve, if you have such kind of a problem, and if now the new person comes in which is recommended by one of the part, okay, and then we need to find out, okay, what type of person he is, whether it's a genuine or not genuine, or should we give on certain kind of things and all these things. So we can use graphical theory. Whereas on the second
So,
side,
sir,
okay, if there is Mhm, mhm.
so we can also we can apply any neural network, any type of artificial neural
Yeah, see,
network
neural
model.
network, I told you neural network, then I need neural network has a fixed structure. Okay, we can use
Yeah.
neural network. So I give the features, and then, okay, I train the network based upon the feature, it will give me the output. That can be done. That, okay, these are the features, then it can detect, it can classify whether the person is genuine or it's a fraud. It can do.
Yes, sir.
But if my features, if there are some variation in the features, then say initially when I developed the neural network for this finding fraud or not fraud, I've taken 4 features. But after that, some some banks give me more inputs. Then what I have to do, I have to then redesign whole of my neural network, because now I have more inputs. Whereas in
Okay.
this case, in such type of cases like graphical, and we have
Yeah.
some kind of a freedom. Okay, so there it is good. They have good level of accuracy also. Similarly, if I say that if I'm taking some person profile, that it's a investing profile, okay, so the person is taking some money in bank every
Yeah.
Thursday and invest something, then take some money, and like, so there is some pattern, and I found that
Yes, sir.
someday there is a lot of money being taken. Okay, so then it is a time stamped basically, or you can say forget time stamp. Then you can predict it that, okay, in December how much money he will invest, put into the bank, or how much he will take out of bank. So then it is a forecasting problem. then you can use LSTM kind of
Okay.
structures. Similarly, you can think of, okay, someday some lot of investment is there or lot of money is being taken, then it can be question mark, like, okay, why it is happening there? So it can be genuine or it can be fraud. So then it's a classification problem. So many things can be done depending upon the data and the problem you want to solve. I hope I'm able to answer your query.
Yes, sir, explained very well, sir. And one more query, sir. So please share
Mhm.
your presentation and the link which
I
you
suggest you
post
go
here.
to, no, go to my website. You will find lot of presentation codes and paper information. Many things you can download it from there. So I've already put all these things there. And if something is missing,
Okay.
then okay, my mail ID is there. You can drop me a mail. I'll happy to share with
Okay,
you.
sir. Thank you very much, sir.
Okay, good night. Yeah. Any more question?
Yeah.
I think no more question, Dr. Ritu. So can we close?
Yes, sir. Sure, sir. So I would now like to request Priyanshi, kindly conclude the session.
Thank you, ma'am. So, I would like to thank Professor Rajesh Kumar sir for imparting us the knowledge about long short-term memory for engineering application and graph-neutral network for engineering application. Also, I would like to thank our Honorable Professor Sunil Kumar Gupta sir, Vice Chancellor Professor Vinay Thapar sir, Head of the Department, and Dr. Keti Chaturvedi sir, Program Coordinator, for organizing such an amazing session. Let me conclude by saying that anything could give rise to smarter than human intelligence in the form of artificial intelligence, brain computer interfaces, or neuroscience based human intelligence enhancement wins hand down beyond contest as doing the most to change the world. Nothing else is even in the same league. Thank you everyone for your patience listening. I appreciate your time and support. Thank you. Thank you, sir.
Thank you very much. Okay, bye.